Hi, everybody. This is Stephen Chu. I'm a professor at Stanford University, and this is a talk that I'm going to give, a public lecture talk in South Korea. And let me just begin by sharing a screen. And so here I go. And here I go. So my talk, let me also minimize this and get it out of the way. Let me put it way in the corner. See if I can get it out of the way completely. Great. So I'm going to talk about the challenges and opportunities in the transition to clean energy and how we can move to a more sustainable future. And this is a real challenge. Meeting the energy and sustainability challenges is a good news and bad news story. It reminds me of the time when a man comes home and very sad look on his face and tells his wife, "Honey, I've got some good news and bad news about our car. What would you like to hear first?" And his wife says, "Well, give me the good news." Well, the good news is our airbags work. And so it goes. So where are we heading and what are the challenges in order to achieve zero greenhouse gas emissions across all sectors? And what are the possible technical and policy innovations? So let's first talk about where we're heading and possible ways to change course. Okay, first we can expect rising seas, increased heat waves, floods, forest fires, droughts, water shortages, and we may see the collapse of fragile nation states due to all these stresses of a changing weather as our climate changes. And this is a map of the world. The darker the red, the more water stress regions are. And this indeed, if it leads to collapse of fragile nation states, will create climate refugees. And the World Bank estimates that possibly there could be 200 million climate refugees by 2050. Here's scenarios where if we have no climate policies, the current policies in place now, there are pledges and targets, and what the predicted temperature will be by the year 2100. And at current policies, what we have today around the world, the prediction is we're going to land somewhere between 2.8 and 3 degrees centigrade. And so that means we're likely going to exceed not only 550 parts per million CO2 equivalent, but actually 600 parts per million, and see roughly a 3-degree increase. But there's other bad news. The effects we've done, the things we see today, and the increased storms and everything else that we're experiencing now is not really what we've already done to our atmosphere. And it's analogous to cigarette smoking. If you start smoking cigarettes, you don't get heart disease, stroke, or lung cancer in your first year of smoking, or even your first 5 or 10 years of smoking. Typically, it takes many years, decades, in order to accrue the damage to your lungs and your full body. How's that analogous to climate change? Well, the bottoms of the ocean are very cold, and as long as the bottoms are cold and there's very slow thermal mixing between the top of the oceans and the bottom of the oceans, think of this oceans as a big reservoir of very cold water, and unless you warm up the water, the full damage is not going to be seen because the surface temperature is being taken down by the cold oceans. So until the oceans warm up to a new equilibrium level, we don't really see the greenhouse gas damage that will eventually come to a new equilibrium level. So that's the problem. The good news is that the cost of renewable energies in various technologies has really plummeted. The most spectacular is solar photovoltaic energy, coming in at roughly 40 cents a kilowatt hour at 2010, and it was even significantly higher than that. It wouldn't even fit on this graph at the year 2000. And by 2021, we see that it's dropped to roughly 5 cents a kilowatt hour. That's averaged over places that have good sun and bad sun. In the best places around the world, it's 1.5 cents per kilowatt hour to even 1 cent a kilowatt hour, including the investments to building the so-called full levelized cost of solar. That's for solar photovoltaic, concentrated solar power also coming down. Wind has been coming down, as you see from this blue line, and even this brown curve of offshore wind is beginning to come down. And the United Kingdom projects that perhaps by 2040, the cost of offshore wind will be competitive with gas before the Russian invasion of Ukraine. Of course, the price of gas now is very much higher, but even before that happened, it would be competitive. So this is all good news, but there's more to it than that, because the wind doesn't blow all the time, the sun doesn't shine all the time. So the full cost of renewable energy includes backup generation capacity, energy storage, and the enhanced transmission distribution you need in order to distribute this power to each country. And so let's look at this and look at the greenhouse gas emissions by various sectors. Energy supplies include, of course, electricity generation, but all other energies that are, let's say, not in industry, building heating, transport, and agriculture, forestry, and land use. So these are major sectors that contribute to the global warming. But if you look at these sectors, in order to get to zero emissions, in the scenarios that I showed in the later graph, of the previous graph, the y-axis is the total emissions of all sectors. And in order to get to 2 degrees, to keep the increase in temperature to 2 degrees, all the emissions have to literally go to zero. That means zero emissions if we still use steel, concrete, use plastics, chemicals, textiles. We grow food. There's considerable greenhouse gas emissions from food. And so the entire food chain has to eliminate its greenhouse gas emissions. And we need to change this mentality of use once and throw away. That goes well beyond paper, plastic, food wrappers, bottles, and shopping bags. Think, for example, of refrigerators. When we think of refrigerators, we can make refrigerators that can last 20, even 30 years, but and make it the repair of those refrigerators easier. But right now, when your refrigerator breaks, for example, after 6, 8, 10 years, the repairman says, well, I can put in a new compressor and there'll be a 6-month warranty. But if you buy a new refrigerator and throw away the old one, put it in landfill, then you get an 8-year warranty. And many people say, well, it's not worth it. I'll just get a new refrigerator. And so we have to change this mentality, and we have to change the idea that we want to fix things and keep them running. But it's also true of home and business furnishings, the furniture, all the other things that go into our buildings. And so the goal is not recyclable, but reusable. Use, instead of plastic water bottles, you just use something you can use over and over and over again to drink your liquids like water. The fundamental change is that we have to think hard about the goal of maximizing the gross domestic produce, GDP, because it really encourages a tear down and rebuild mentality. For example, if you build something that could easily last 100 years, like a building, typically we don't build modern commercial buildings to last 100 years. We're expecting to tear it down in 50 years and build a new one to modernize the heating, ventilation, and cooling systems, whatever systems there are in telecommunications, but you don't have to do that. Let me give you an example. First, we know how to make very old buildings. The Forbidden City in Peking, where the emperors of China live, wooden buildings are over 600 years old. Well, you say that this is, a palace, it's very special, it's not a commercial business. Money wasn't an object, and it is lavishly restored. So let's look at modern buildings. So I chose 3 modern, American buildings: the Empire State Building, the Chrysler Building, and the Chicago Merchandise Mart. They were all built in 1930, 1931. And yet these buildings are still being used today commercially. They're not museum pieces, and they're used as office buildings. Now, the renovation of these buildings costs a lot of money because the buildings were not designed to modernize heating, ventilation, cooling systems. Then they had older windows. Today, we can make very good windows. In fact, dual pane with vacuum gap windows that would have the insulating capability of 6 inches of insulation. And so if we build a shell and a structure of the building that could last 100, 200 years, we can also build them to modernize things as needed in the interior. This is what we need to do. I also already mentioned the electricity transmission and distribution has to be much better because we are going to have intermittent generation of wind and solar power. These energy sources have less what we call magnetic field inertia. If you have big spinning generators with a lot of steel inertia built into these things, if you've taken any electricity and magnetism courses, you'll know there's a Lenz's law which stabilizes the voltage and the currents that go through these big rotating generators. That automatically stabilizes the grid, and photovoltaics don't have that. So we're going to need an active control to stabilize the frequency and voltage. But there's more than that. We're expecting to have increased electricity dependency on transportation. Where we can, we want to use electricity in industrial heat processes, commercial and residential heating instead of natural gas, and cooking in restaurants and homes. But if we do this, if electricity is going to supply all of these things, as well as lighting and air conditioning, that's going to reduce the resiliency that used to come from multiple sources of energy. And so the supply of turn-on sources of energy will also decrease. So again, as we go towards renewable energy, we have to ensure that the system is going to be robust and we're not going to have significant blackouts for long periods of time, long periods being days. So energy storage is key to all of this. Here's a picture of my favorite battery. It's an old style Midwestern United States, 150-year-old windmill. And the way it works is when the wind blows, you pump water from underground into this water tower. That's the energy intensive thing you need in order for irrigation. And when you want the water, you open a valve, and that takes very little energy. And so this is a way of converting transient, intermittent wind or solar energy into something. You lift water up a hill, or you use the energy that you can easily store. And if you can use it, for example, solar power, wind power to disinfect water. And once it's disinfected, the energy's there, it doesn't get, the water stays clean. And so again, you don't have to have energy on demand water. The United States is blessed with considerable renewable energy in the forms of wind, solar, geothermal. But in order to achieve 80% renewable energy in the United States, it turns out we would only need 3 days of energy storage. And what that means is the entire electrical system storage battery storage should be capable of running the entire United States for 3 days. So that's a certain amount of energy. And it happens to be about 2,000 times more battery storage than we have today. But in addition to that, in order to remain competitive with natural gas, this techno-economic analysis by 3 former DOE members estimated that in order to compete with natural gas, the cost of stored energy has to be $10 to $20 per kilowatt hour. Right now, utility scale batteries cost about $300 a kilowatt hour. It will likely, in the next coming 2 decades, go down to $100 a kilowatt hour. But what that means is you still have to drop by another tenfold in price to get to $10 a kilowatt hour. And this is not going to happen in the next 10 or 20 years. It will require a significant breakthrough in battery technology. Cost of EV batteries for vehicles is a different story. These batteries don't have to be as reliable as utility scale batteries. They really have to have a very low probability of failing because it would lead to blackouts, and the utility companies want them to last at least 30 years, not 10, 12 years. And so this is the energy storage by energy per unit volume on the y-axis, energy per unit weight on the x-axis. So the upper right-hand corner of this graph is good. This is low energy. This is their standard lead acid battery that's hundreds of years old. This circle is the Tesla battery used in the S1, and we're expecting that the batteries will increase in energy density, smaller batteries, lighter weight batteries, and we're expecting that perhaps by 2030, we could see an increase of 2x. This is all good news, but if you think about utility scale batteries, we have other issues. For example, if you want to store batteries not for a car, a light-duty vehicle, but for utility scale that lasts weeks, months, and seasonally, we simply don't have the materials that can do this. So again, this is a real challenge. But the continuing good news is we're seeing a very rapid rise in the acceptance of electric vehicles around the world. It's a few percent of new car sales now, but it's predicted that by perhaps 2040, roughly half of the new cars would be electric vehicles. Well, that's 2040, we're 2022. But the other news is that by 2040, even if half the sales are electric vehicles, the rest are internal combustion engine cars, and they will last another 10, 15, even 20 years. And so by 2040, it's predicted only a third of the vehicles on the road would be electric vehicles. The point of this is a transition to clean vehicles from internal combustion engine cars will take many decades, not just 10 or even 20 years. So what about the materials? Well, already, because nickel and cobalt are very expensive, battery manufacturers are already transitioning to iron phosphate type of batteries, iron batteries, but they're still using lithium. Meanwhile, lithium has increased in price by a factor of 4 in the last couple of years because this huge increase in the demand for electric vehicle batteries is driving up costs. Now, lithium turns out not to be rare. It just happens that the methods we use now of taking very salty water from underground, putting it in lakes, letting the salt evaporate and extracting lithium from these brine deposits is very polluting and expensive. It takes a few years to evaporate the water. And if you could take these salty lakes, but not expose it up ground, but just bring it up, filter out just the lithium and put it back underground, it would be far less polluting. Ideally, if you could take lithium from seawater, and that's challenging because the ratio of sodium to lithium is in the ratio of 1 to 20,000. There are 20,000 times more sodium molecules than lithium molecules. And so the extraction method has to be pretty good. But if you can extract it from seawater, you've just increased the supply of lithium by many thousandfold, perhaps 5,000-fold. And it could be very much less polluting. This is Chong Lu, who is a postdoc co-directed by Yi Shui and myself, who we published an article in 2020 that's the first attempt to recover lithium from seawater. It works, but this method may or may not be commercially viable because you have to cycle this material that captures the lithium but rejects the sodium, not 10 times as presented in the paper, but you actually have to cycle it hundreds or thousands of times. Even though the material is very inexpensive, it would not be practical to be changing material out, in and out. So for that reason, we're working on other ways to improve this, to extract lithium in a practical way in large quantities from seawater. So we're not there yet. It's not commercially viable at the moment, but there's hope that it will be. Going back to pump storage, lifting water, pump storage means you have an existing hydroelectric dam and you put a little pond below at the bottom of the dam. It only has to be 1% or even less of the full reservoir behind the dam. And so what happens is you store this water, and if there's excess wind or solar power, you can actually run the turbines in reverse, pump it up the hill. And if it's a 100-foot drop, what you find is pumping the water up the hill and then regenerating electricity as you let it flow back into the pond could be 75% efficient, about as efficient as commercial flow batteries, but in a much larger scale. Now, in 2021, China leads the way in terms of power generation, over 36 gigawatts of power generation, followed by the United States, about 22 gigawatts, and Japan also nearly 22 gigawatts. Both China and the United States have ambitions to greatly increase the amount of pumped hydro storage. China wants to more than double it. Right now, we have applications for pumped water storage projects that, if they're all built, will add another 19 gigawatts to the 22 gigawatts. So it would be nearly double. And so China and the United States are beginning to realize there's a real opportunity to get this seasonal storage. We need it. Of course, a lot of attention has been played to hydrogen. Now, there are various colors of hydrogen. If you take the way we produce hydrogen today is you take natural gas, methane, and you convert it into hydrogen and CO2, and we vent the CO2. So burning hydrogen, yes, there's no carbon emissions in the burning of hydrogen. You just make water vapor when it combines with oxygen, but the carbon dioxide emissions from burning natural gas or burning hydrogen is about the same. And so you're not saving any carbon emissions if you vent the CO2 to the atmosphere. There's blue hydrogen, which means you get the methane, you convert it into hydrogen, and then you put the CO2 underground. But that means very large-scale CO2 carbon sequestration, and those are unsolved problems at the moment. The cost of blue hydrogen compared to gray hydrogen is maybe double the price. And finally, there's green hydrogen using wind, solar, or nuclear reactors, which also don't have carbon emissions. And that is using electrolysis, but right now the electrons are expensive, and it's maybe 4 times the price of gray hydrogen. And so we need to lower the price. But the good news is that hydrogen can also be used to decarbonize steel production, decarbonize the plastics, chemicals production, and the making of fertilizer. And so right now, the basis start of fertilizer is natural gas. But the electrolyzers, if you're going to use green hydrogen, the costs are too expensive. They have to be reduced, and they have to operate at high current densities. The high current densities mean higher voltages, which means it's less energy efficient. And so you have to design electrolyzers that can work with these very high current densities, but with not much over potential. There's something alarming that's been discovered in the last year. It's found that hydrogen, when in the upper atmosphere, actually keeps the UV light from breaking down methane into carbon dioxide. Now, methane is about 80 times more potent a greenhouse gas than CO2, but it doesn't last for a very long time, maybe 20 years. Whereas CO2, we think, once up there and circulating between land, oceans, and the atmosphere, could last thousands to tens of thousands of years or longer. So, but nevertheless, methane emissions are very, very potent greenhouse gases. And if hydrogen is going to increase the methane emissions, this could be a very significant global warming effect. It also damages the ozone layer, and it produces up high clouds that also produce a greenhouse gas effect. So this is a real issue if we do large-scale hydrogen production. Hydrogen is very leaky, and we don't have a good way of detecting the leaking of hydrogen. It requires an instrument called a mass spectrometer, which means you actually ionize the molecules in a vacuum and bend them, accelerate them and bend them in a magnetic field. And you can actually tell from how much they bend that this is hydrogen. Very costly detection mechanism. And so if you imagine putting in a pipeline distribution system that pumps hydrogen around the way we pump natural gas, right now, that would not be a good thing. And there's a realization that we cannot build hydrogen distribution lines because there will be 2 or 3% that leak out. How do we know this? There's 2 or 3% of natural gas that leaks out of our American pipeline systems today. And methane leaks are much easier to detect. They're very inexpensive means of detecting methane, and yet we still leak 2 or 3%. If we massively convert to hydrogen, that 2 or 3% would be very dangerous. Finally, in order to get green hydrogen to be competitive with gray hydrogen, you need a price on carbon, because we don't see it coming down fourfold in the next tens of years, 20 years, unless the full cost of venting CO2 is paid for. Now, of course, the real challenge is you capture carbon dioxide from the atmosphere and you convert CO2 and water. It could be thermochemical, electrochemical, photochemical, biochemical, we don't care, as long as all those energy inputs have no CO2 emissions. So what you're really doing is you're taking the combustion products of hydrocarbons, which ends up being water and CO2, and you're converting it back into an energy form, starting with hydrogen and CO. But of course, what we'd really like to make are liquid hydrocarbons. For example, the liquid hydrocarbons we use for diesel fuel, aviation fuel, gasoline. Those are very high density fuels. And sustainable aviation fuel that doesn't compete with land use is still a big challenge. The price is roughly 4 times more expensive than pumping oil out of the ground and turning it into diesel or aviation fuel. But there's something more important, even as important, I should say, with liquid hydrocarbons. For example, this is a supertanker, and the supertanker can hold crude oil. It can ship it halfway around the world. You can unload the crude oil in oil tanks in the country that's going to use it, so you have a little bit of energy security. And if you ask, when this crude oil is converted into gasoline, how much are the transportation costs on a per dollar basis for the transportation and storage of crude oil? And the answer is 2 cents a gallon of gasoline. So the additional cost of transportation and storage is very, very small compared to the full cost of gasoline. And so think of these super tankers as intercontinental energy transmission lines that can span oceans. And so the idea of converting energy in the form of solar, wind energy, geothermal energy into a liquid hydrocarbon, so put it on a tanker, converting economically and putting it in a tanker is a long-term goal. Again, we don't know how to do this today economically. We will need compact on-demand energy sources because our batteries will take decades to develop for seasonal storage. And so what do we have today? Well, our current choices are natural gas, chemical, like hydrogen, and nuclear power. Now, there are downsides to all of these things. Natural gas means you have to capture the carbon dioxide and sequester chemical, hydrogen. There's these issues beginning to emerge with hydrogen. It doesn't mean we shouldn't use hydrogen. We just can't put it in pipelines. And finally, there's nuclear power. Now, people are afraid of nuclear power for various reasons. They consider it unsafe, for example. But recently, California, which these are the last two nuclear power plants in California, maybe 50, 80 miles south of San Jose. And the current governor of California, Governor Newsom, ran on a platform saying he was going to shut down the nuclear power plants. The legislature wanted to shut them down. The utility companies decided the public was so against nuclear that it's not worth fighting, so they were going to shut it down. Now, in the last 2 or 3 years, some of us, including myself, have been trying to work with the powers that be, the governor and other people, to try to explain that without nuclear power, it's going to be much harder to reach our carbon emission goals. Right now, California is a leader in the world. It's the 5th biggest economy of the entire world, just California. And yet we are now 70% electricity generation carbon free because we have a lot of solar, we have wind, we have hydro, and 10% of it comes from nuclear power, just these 2 reactors. And so we want to go to 80% and more. We have laws that will outlaw internal combustion engine vehicles by 2035, very soon. And so we're moving as briskly as we can, but we still need clean sources of electricity. That means as we transition to electric vehicles, the electricity that powers those vehicles will also be carbon-free. Now, what about the dangers of power production, energy production? Well, the most dangerous is brown coal, lignite coal. The second most dangerous is black coal. And in terms of the number of deaths measured from accidents and air pollution per terawatt hour, you have 32.7 deaths from brown coal per terawatt hour, black coal 24, oil 18, burning biomass, which was considered green, you have 4.6 deaths per terawatt hour because of the air pollution, followed by natural gas and then hydropower. Here's nuclear down here, 0.03 deaths due to radiation in the uranium mining and some releases of radiation, but including Chernobyl and Fukushima. Fukushima, the projection is there will be about 200 premature deaths due to the radiation leak from Fukushima, but yet that was enough for Japan to reconsider, shut down all the reactors, and for a while thinking instead of being 60% nuclear power, they're going to go to 0%. Now they've reconsidered what that costs. They started building coal plants, and in terms of the dangers to society, there is no comparison. So you have nuclear down here at 0.03, and you have coal at about 30. Okay, that's a factor of 1,000. Nuclear is safer than hydropower because hydroelectric dams occasionally break and people drown. It's slightly safer than wind, but the difference is not really relevant. Why is wind dangerous? Well, people who build wind turbines can fall off during construction or servicing. So the dangers of nuclear power are very small. It's some of the safest forms of energy on a per energy and death basis, and yet people are still very scared of it. The long-term sequestration of spent nuclear fuel is a solvable problem, especially with new deep mining techniques, automated techniques. And so society, this is developing rapidly. The pioneers in this are Finland and Sweden, but it is a solvable problem. Okay. What's the problem? There's another problem with nuclear. The cost of nuclear power plants has gone through the roof. In the United States, the cost of building a nuclear power plant has gone up tenfold. And it went up since 3 Mile Island. So we need to learn how to construct safe nuclear power plants at the original costs when they're first being developed. Even reducing the cost by a factor of 4 would change completely the investment thinking of nuclear power plants. But it's these very high costs that are driving things up. And so, again, you still want the nuclear power plants to be very, very safe. There's an opportunity, for example, to build a small modular plants built in a factory under very controlled conditions, mass produced, so there are no construction delays. You ship out the reactors on a truck, on a boat, and you run them for 5-10 years, and then you refuel them by shipping them back in the factory as another possibility. But certainly just shipping them out there, if you refuel them out there, at the very least, you can reduce those long construction delays that lead to bankrupt power companies. So let me talk about more unintended consequences of the Industrial Revolution and agricultural revolutions. In the agricultural space, there are greenhouse gas emissions of CO2 from diesel tractors, methane, I'll talk a little bit more about that, N2O, from fertilizer and fluorinated gases. And these are potent greenhouse gases that are changing our climate. And so we'll need a fourth agricultural revolution. So what do I mean by that? Well, I'm going to give you a little history lesson. But before I do, I'm reminded of this quote: "Those who cannot remember the past are condemned to repeat it," by a Spanish-American philosopher, essayist, novelist. And in this cartoon, this fortune teller says to the woman, "You will make the same foolish mistakes you have made before, not only once, but many, many times again. And for that reason, you have to pay attention to history." Now, this history is a very simple history. It's the history of climate over the last 400,000 years. Present day is where my pointer is at 0, and going backward, this is taken from ice core samples in Antarctica. There were ice ages. There was a previous warm period. During this warm period, about 2 degrees warmer than we are today. Sea level was several meters higher, 3 or 4 meters higher. Another ice age, warm period, ice age, warm period. Now, these changes in climate had nothing to do with humans. There was no carbon emissions for all this period. And but something happened. Now, before I go on, let me tell you, why is climate change now different as the globe is warming up? Since the climate changed for 400,000, indeed it changed for tens and hundreds of millions of years ago. This is different because the carbon in the atmosphere today is being diluted of the isotope of the carbon, carbon-12, the predominant isotope of carbon. There's also carbon-14, which is made in the upper atmosphere due to cosmic rays. And so this carbon-14 is radioactive. It lasts 5,700 years. It diffuses down to the biosphere. We have carbon carbon-14 in ourselves. Suppose we die and are put in a coffin that's well sealed from the environment, so it's not mixing with the environment. And then maybe 100,000 years ago or a million years later, we're exhumed, and there are a lot of us, and we're being used to generate power. So this is a source of carbon, us, and we're being burned like fossil fuel. Well, if we've been sequestered away from the environment for hundreds of thousands of years, and the lifetime of carbon-14 is 5,700 years, there is no more carbon-14. And so when you introduce this carbon into the atmosphere, you're diluting the amount of carbon-14 to carbon-12 ratio. The dilution is quantitatively in agreement with the amount of greenhouse gases that we produce from burning fossil fuel. So this is the smoking gun that says these have human fingerprints all over it. We've taken sequestered carbon in the form of fossilized energy, gas, coal, oil, burned it. It has no carbon-14 in it. Now, let me expand over the last 12,000 years. And if we expand over the last 12,000 years, we find that the climate was remarkably stable and warmer than the ice ages. But during this time, about 12,000 years ago, agriculture started, not only in the Fertile Crescent of the Middle East, but also in North and South China, New Guinea, Ethiopia, the Americas. So what happened? One conjecture is the climate became stable. And when the climate became stable, you could develop agriculture. What we're afraid of, and what the climate models are telling us, is in this global warming, the climate may become more unstable. And we might see more temperature variations. But in any case, the climate was stable. And for the first time in Homo sapiens history, this allowed us to start to domesticate plants and animals, grow food, instead of hunting and gathering and roaming. And so in this summary of the development of a civilization and population, Nobel Prize-winning economist Robert Vogel starts his summary history of the beginning of the first agricultural revolution, includes the invention of the plow, first irrigation, the beginning of writing and mathematics, populations puttering along. There's the peak of Rome, the peak of Greece, beginning of the second agricultural revolution, something remarkable happens, and the beginning of the Industrial Revolution. So what are the first agricultural revolution? Well, it's domestication of wheat and rice, cattle and chickens. It's yeast for bread. These are the times when it started. The first irrigation, and the fermentation of grain and fruit juice into beer, wine, and spirits. So these are technical advances that enabled us to transform sunlight into food to feed a growing population. But what about the second agricultural revolution? Remarkably, the second agricultural revolution were largely policy changes. For example, before this, everybody had access to the land, what are called common rights access. And starting in Great Britain, they said you're allowed to put a fence around their land, and only the owner of the land can use the land. People didn't have the right to bring in their cattle, their horses, their whatever, and use the land. And so for that reason, food production went up. It stabilized because there was a caretaker of the land. It also led the development of tariff-free markets, better transportation infrastructure, roads, canals, railways, and the movement of food and goods produced a system that made agriculture productive. So this tells you how important policy changes are. Now, what was the third agricultural revolution? Well, it was the ability to synthesize ammonia, ultimately from nitrogen in the air. And the invention of that led to a Nobel Prize for Fritz Haber of the so-called Haber-Bosch process, and that in 1918, but Karl Bosch, who worked with Fritz Haber, got a second Nobel Prize in 1931. Well, it couldn't be for the ability to synthesize ammonia, urea, and fertilizer, but it was the same process. It was called the Haber-Bosch process in 1918. So they had to think of another reason, and they said, we'll give it to Karl Bosch for the invention of high temperature, high pressure catalysis. But the two collaborated at the very beginning. Anyway, that led to artificial fertilizers that were able to feed a growing world. There was another part of the agricultural revolution where people took strains, starting with strains of wheat, but followed by corn, by rice, by all the major grains. And this was spearheaded in the 50s and 60s by Norman Borlaug, who bred strains of wheat so that the kernels of wheat would be much, much bigger and fatter than the normal previous strains we were using for hundreds and thousands of years. But the grain kernels were so heavy that their weight would fall over, so he bred in what are called dwarf strains of wheat, with very thick stems to support the heavier kernels. He bred in something that was more resistant to stem rust fungus, a disease of the plant. And he bred in the ability so that these grains could sustain heavy fertilizer and irrigation use, and they would grow. And so this revolution with the fertilizer revolution meant that between 1960, when the population was roughly 3 billion people, to 2016, when the population was 7.4 billion people, the land put under cereal production, wheat, rice, other cereals, remained flat, whereas the cereal production went up more than 3.5-fold around the world. In the United States, corn production went up 7-fold per acre. And so this revolution meant that we could grow, feed a growing world and have more food. Already the land use is now, half the arable land is now put under cultivation. And so this is a real revolution. And what do we need now? Well, we need better stuff. Now, I've talked about Norman Borlaug generating crossbreeding strains of wheat, but we've been genetically modifying plants and animals for over 4,000 years. For example, if you look at the breeding of wild corn into modern corn, and you look at the wild corn and the modern corn, you realize that the corn found in the wild looks nothing like the corn we eat today on the left-hand side. Very much more productive. And so we've transformed this thing into a real engine for converting sunlight, water, nutrients into food. We've also bred animals that we eat: beef, cattle, pigs, chickens, turkeys, for example. The full circle indicates the natural lifetime of these animals, but the little red segments are the time before, from birth to slaughter. Beef, for example, in the United States, 18 to 24 months before slaughter, the average cattle, after you've taken out the guts and everything, which is the so-called dressed amount of weight, is 1,500 pounds. Pigs, after 24 weeks, the average weight of a pig is 280 pounds. Chickens go from hatching to the time they're slaughtered for sale, only 40 days. Turkeys, also very, very short. So this livestock has been bred to grow very fast in a small fraction of their natural cycle. These are pictures of American domestic turkeys. They're very breast heavy. In fact, some of them are so breast heavy they can't mate. And so they're made by artificial insemination. 20 pounds, 15 or 20 pounds, excluding the guts of the bird and the head and the feet, in just 3.5 months. So these are our, American domestic turkeys. These are wild turkeys of unknown ages. Look very different, heck of a lot smarter as well. And of course, unknown ages, but we have wild turkey whiskey, bourbon in the United States, and we know exactly how old this wild turkey is. Okay, moving along, let's go back to animals. If you have beef or dairy cows, there are microbes in their stomachs that take the food that they eat and turn it into, they metabolize it, and the byproduct is methane, and the animal burps out the methane. This is not a symbiotic relationship, it's actually parasitic. These microbes are mostly stealing the food from the cattle. We know this because we can feed the cattle, for example, forms of seaweed that decrease the methane emissions by 90%, and the cattle are just fine. They just don't like the seaweed, but they grow just fine. So if you look at agriculture and garbage, a lot of it being food garbage and manure management, you see that the majority of methane emissions around the world is due to agriculture and food waste compared to natural gas and petroleum systems. So methane is a very big deal in the animals we eat. To convince you how big a deal this is a graph of carbon emissions starting in 1750 to 2020. This is the world carbon emissions. By 2020, China's carbon emissions is more than the United States and the European Union and Great Britain and India combined. But India is going to be turning on. Meanwhile, the projections are China will also be going up. And so it's the rise of the developing world that are increasing the carbon emissions. Of course, before the 21st century, which is about where my cursor is here, the lion's share has come from the developed world, the United States, EU. But since about 2080, China has really begun to contribute. Anyway, going back to animals, if beef and dairy cows were a country, and we looked at their greenhouse gas emissions, we find that just the greenhouse gas emission equivalent just from beef and dairy cattle are more than the United States or the EU plus European Union plus Great Britain. So that's a significant amount. We've also bioengineered the world in profound ways. If you put on one side of the scale human biomass and all the animals we eat and compare it to all the rest of mammal mass. So this is deer and squirrels and rats and mice and you name it, lions and tigers and bears, all the mammal mass. We are 96% of all mammal mass today, people and the animals we eat. And so it's an amazing geoengineering feat. And in the production of the food, the animal feed, and the greenhouse gas emissions from the animals themselves, we have a lot of greenhouse gas emissions. Leading the way are beef. This is greenhouse gas emissions per prorated per kilogram of food that we actually eat. And you see the beef and lamb lead the way because they have these microbes that make them burp. If you compare that to pigs and poultry, chickens, or farm fish, it's very much a smaller fraction of what we have in beef. But of course, the best thing is to go to rice and tofu and other things. Milk, this is not including, this is the milk, but not including the dairy cow. So anyway, and the grains are much, much better. So the trouble is when developing country gets richer, they want to develop American diets with many more meat and a lot of beef, and this is not going to be sustainable. Catching of wild fish in the oceans and rivers and lakes is not sustainable. And most of the fish the world eats today are farmed fish. And there are issues with the fish, but this is wild salmon. we can actually alter the salmon. If we take a very rapidly growing salmon and put in that rapidly growing salmon one gene from an ocean pout, the salmon can feed all year round and they grow much faster. And so this is the wild salmon, the rapidly growing salmon, and this is the salmon with the one gene from the ocean pout, and it can grow all year round. So substantially bigger, 4 or 5 times more weight. Approval process took 20 years. They want to make sure that these type of salmon would never escape into rivers, lakes, streams, and oceans. They had to be in contained tanks, and the tanks' water had to be really filtered, so there's no chance that the DNA from the salmon would leak out. But this is, again, what genetic modification can do. But look, what about all our food crops? Well, there's a significant amount of nitrous oxide emission, N2O, from fertilizer. Lion's share of N2O emissions, another potent greenhouse gas, in the same class as methane in terms of how bad it is due to agriculture, soil management, wastewater, and other things. And again, agriculture is a major supplier. And of that, it's fertilizer, overuse of fertilizer, which causes algae blooms, but it also causes N2O emissions. So what can we do? Well, there's a new field of science emerging out of biology called synthetic biology. And that's where you alter genetically, not just putting one gene like the ocean pout gene, but you put in dozens of genes. And then with these dozens, 10 genes, 5 genes, you can maybe get the microbes to start to make plastic material, maybe fuels for airplane. But one application is you can actually alter microbes so the microbes enter into a symbiotic relationship with plants like corn, and or you can put something that you cannot do by plant breeding into plants so that you don't need insecticides. This is an example of this. It's called BT eggplant. The BT is from a common bacteria, and it's found that this common bacteria emits molecules that insects don't like. And so this is a naturally occurring insecticide, not harmful to people, doesn't taste like anything, and has been in use for 9-10 years, going on 10 years. First, finally, regulatory approval was given after considerable testing, and now the farmers in Bangladesh love this stuff because the insecticides are poisonous to them and they're very expensive. And the BT eggplant, which is resistant to these worms that ruin their crops, is great. So this is an example of genetic engineering of one gene. But here's an example of genetic engineering where there are a whole bunch of genes. And these genes are put in microbes that land on the interface of the corn roots with the soil. And these microbes take nitrogen from the soil that comes from air, and they turn this nitrogen, naturally occurring nitrogen, into fertilizer type food that the corn uses to eat. And in return, the corn gives the microbes something. So it's a symbiotic relationship of the corn and the microbes, very much like soybeans, which have some symbiotic relationships with their microbes that require virtually far less fertilizer. A startup company called Pivot Bio has altered the microbes so that you use only half the fertilizer of corn. This is normal corn. This is Pivot Bio corn. The goal is, of course, to get rid of all the fertilizer, the nitrogen-based fertilizer, and also phosphorus and potash production in the same round. Pivot Bio is now working on sorghum, and very exciting. This company collaborated with a company I was on the board of directors with called Zymergen, which was using robots and machine learning methods to actually try to get the process much faster. And in one lucky example, where this was a microbe used in industrial production from a company, a big agricultural company, the Zymergen started with something, and only in 1.5 years, it increases production considerably. But this is a unique case. The average time Zymergen needs in order to alter the microbes to produce something you want, whether it's a thin film that replaces some hydrocarbon for cell phones or pivot bio type microbes, it takes typically a half a dozen years. Why does it take so long? Well, the current recombinant technology that introduces genes into microbes allows the insertion of only one gene at a time. After you've done that, and you need, let's say, 5 or 10 genes, and you want the correct mixture, you've got to insert them one at a time, and then you've got to look at combinations of these. By going round and round, each time you do this, it takes months, and so you have to do many cycles. If you can insert 10 or 20 genes at a time, it's totally different, because we've had the technology to produce any gene we want by pure synthesis of DNA, but we couldn't get them into cells, except by using, for example, virus transvections or other methods that only produce very, very small snippets of DNA, maybe up to 10 kilobases. So very recent, we've demonstrated that we can put in 50 kilobases of DNA into cells, massively parallel with high cell survivability. I think that we can go to maybe 100 kilobases, but even 50 kilobases mean you're now talking about, including the overhead and everything, instead of one gene at a time, you're talking 5, 10 genes at a time. So a very, very big deal, which means you can actually experiment with the right combinations in a combinatorially fast way. And so we hope, we're about to publish and submit this, or submit and publish, I guess it goes in that order. And if successful, then the synthetic biologists can use it. Now, in the end, we have to capture greenhouse gases from all the things that generate greenhouse gases today. This is cement manufacturing, steel plants, production of chemicals, plastics, and so on, in addition to power generation from fossil fuel. So carbon capture will be needed. But as I said before, we're likely to go over 550, even 600 parts per million CO2. And this is going to be really bad. And so we've got to bring the CO2 in the atmosphere down from 600, 550 back to 400, or even really back to 380 parts per million in order to restore the damage we've done before the glaciers in Antarctica and Greenland melt. The glaciers in Himalayas and other places around the world are melting a lot, but it will take hundreds of years for the glaciers in Antarctica and Greenland. And so to melt and increase the sea level rise by 10 meters or more. And so we need carbon capture. And so carbon capture means, like the first law of holes, if you find yourself in holes, stop digging. So that means stop the carbon emissions, capture carbon emissions for our current processes until we find a way of producing the steel, the cements, the plastics, the glass, the paper, everything in a carbon-free way. We're also trying to invent better ways of capturing carbon. This is one of several new startup companies. Svante I'm on the board of directors of this company. I'm also doing research with others at Stanford on even newer ways of capturing carbon than this company is pursuing. But in any case, this has become a very important goal in order to lower the cost of carbon dioxide, not only from, for example, a plastic or cement plant, but you've got to lower the costs of capture from the air. capture costs right now could be $300 per kilogram of carbon dioxide captured from the air. It's got to reduce before below $100, even $80 before people will consider carbon capture. And we have to develop better sequestration methods. The best carbon capture is plants. The crops we plant on a yearly basis capture 30 billion tons of carbon dioxide a year, but virtually all of that carbon dioxide is recycled. The plants die, we use the plants like wheat straw, rice straw, other things, becomes carbon dioxide again, or they rot and it becomes worse. It becomes methane and carbon dioxide and goes back into the atmosphere. And so the whole of global human emissions is 40 billion tons of carbon dioxide a year, add another 12 if you consider methane, N2O, and other potent greenhouse gases. And so we have in plants solar-powered carbon capture machines. The question is, can we take the residual biomass that we don't eat and instead of burning it, turn it into something useful, or just turn it into something that won't turn into carbon dioxide or methane, which means you've got to keep the microbes away from this material, which means you take the biomass, you dry it out, you compact it, you sterilize it, you put it in a big plastic bag, and we can make plastic that's really non-biodegradable for hundreds, perhaps even thousands of years that won't go into microplastics. And so that we know how to do. So is it possible to take all the bioresidues from the plants we use for food and for animal feed, and that would easily be gigatons per year. And in any spare land, we can actually plant plants that are actually 5 times more productive per unit area than the food we eat. These are weedy plants. This is a plant called switchgrass that grows like a weed in the Midwest of the United States with much less water and nutrients. And that's not a midget, that's like a 5'8" person standing in a field of switchgrass. So these are technologies that we don't have in hand that are economically viable, but these are technologies we're going to need. But in the end, we still have a population growth. It took 1 million plus years for precursors to Homo sapiens. Homo sapiens, in the last couple 100,000 years, to grow to a population of 1/3 of a billion. From that time, in the next billion, we're adding 13 years per year at the current rate. We're now, when this chart was made in 2011, we had a population of 7.2 billion. We're now 7.8 billion. We're now projected to go to 9 billion in another, by 2050, 9 billion from 7 billion in 2011, and 11 billion by the end of this century. This is an issue because technology is not going to save us again and again and again. The other issue is that all economies are based on the fact that when you have more young people and fewer older people, the younger people are the productive members of society and they can support a smaller aging population. So the whole economic system is based on population growth. In the United States, we call this a pyramid scheme. It's a fraudulent way of making money by recruiting ever-increasing number of investors, and you buy more new investors that you can use the money to pay off the old investors, and you don't have to have a sustaining profit-making machine. And so we've got to change this. Now, people all over the world are choosing to have fewer or no children once they go and get into the middle class and the upper class. So this is a natural population control mechanism due to many reasons: education of women, better things to do at night, like watch TV or read books, because we have lighting. And so we should let the population decline naturally. The other thing is that we need a different measure of wealth. I already said the push to increase the GDP means it's a push to build, use, consume, throw away, build more. And the production and consumption of more stuff is not really things that lead to ultimate happiness, because if you think about what wealth and quality of life mean, it would include physical security of yourself, your family, your loved ones, longevity, but not only living longer and healthier, and having quality health and mental activity, which means continuing education and access to learning, possibilities of learning well into your 70s and 80s and even 90s. Elimination of long hours of commuting to and from work, but not staying at home and Zooming with people. But human contact turns out to be very important for emotional stability and emotional civility. And so these are the things we value, not just GDP. Now, I'm going to conclude by two references. One is one of my favorite pictures. It's Earthrise from Apollo 8, taken on Christmas Eve, 1968. And in the last orbit around the moon, the capsule was heading back to Earth, and the astronauts stuck a camera near the window and took this picture, which is called Earthrise. And in this picture, you see Earth and you see the moon. And from this, you can tell the moon is not really a good place to live. There's no water, there's no air, there's no magnetic fields. The shield is from the so-called cosmic rays, most of which come from the sun, but also from the cosmos in general. And this Earth from this photograph looks beautiful. And there's something else, black everywhere. And the astronaut who took this picture said, "We came all this way to explore the moon. The most important thing is we've discovered the Earth." And we discovered how precious it was. And since 1968, we've also discovered that the industrial and agricultural revolutions are changing the destiny of the Earth. And there is nowhere else to go. And the final two slides are a picture taken by Voyager 1 as it was leaving the solar system. And this is a schematic, not to scale, of the inner planets, Earth, Venus, Mars, Saturn, Uranus, Neptune. And as this Voyager went past all the planets and past Neptune, and it turned back to Earth. And it took a last picture before, this is 40,000 times the radius of the distance from the Earth to the sun, 40 times the distance of the Earth from the sun. And it took this picture of the so-called pale blue dot, which is Earth, seen by this exiting Voyager 1. And I'm going to play you what Carl Sagan, an American astronomer, said about this.
From this distant vantage point, the Earth might not seem of any particular interest. But for us, it's different. Consider again that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate or joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on the mote of dust, suspended in a sunbeam. The Earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all those generals and emperors, so that in glory and triumph they could become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe, are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit? Yes. Settle? Not yet. Like it or not, for the moment, the Earth is where we make our stand. It has been said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known.
So anyway, with that, I conclude and I will stop sharing. And I hope this talk opened your eyes, gave you food for thought, and perhaps some optimism, but also some realization that the challenges we face are enormous, but we have to meet them. There is nowhere else to go. And so with that, I will end and stop the recording. Thank you. Bye.